3 years ago, he was one of the authors of a report of the National Academy of Sciences, which talked about early childhood and the development of mathematical understanding. And it really shifted the attention of the research community and indeed the world about how quickly and how comprehensively the human mind develops numeracy, the ability to understand numbers in mathematics and quantitative skills. And Herb has been very central to the scientific endeavor of opening up that field of study. He's done this through NSF grants, through the dissertations of his students, through as many publications and research study of his own. And out of that has come a kind of play, where he also has been developing games, ways that children and teachers can interact with one another, archives of videos, looking at how that interaction takes place. And so he's created this whole body of work now that is also translational. It's moving into ways that teachers and students and parents and kids can work together to accelerate and expand mathematical understanding. And with that, I introduce Herb Ginsburg.
I'm going to talk to you tonight about Adventures in MathemAntics, which is our new software. And we call it MathemAntics because it has an antic quality. It's not drill. It is hopefully a lot of fun, although we know that math and other good things don't always have to be fun, and in fact shouldn't be. I want to acknowledge the several sources of support that we've had. The Cleveland Dodge Foundation has been supporting us over the past several years, and particularly in the form of fellowships for 4 of our students. There's the Institute of Educational Sciences of the federal government. And all of that has allowed us to produce this team, some of whom, I can't see everybody, but Ama Awatwi is not here, I think. No. Kara Carpenter, Samantha Crayon is over there, Azada Jamalia, and Rachel Lebrecq, Dana Pagar, and Esther Yun. They've been a wonderful team, and we are working with a group in Boston, in the Boston area, particularly with Jonah Elgart, who's a designer, and Doug Martin, who is a programmer. So I want to acknowledge their contributions to this. So what's the problem we are trying to deal with? Math education is really shortchanging our students, particularly the poor and disadvantaged. In the US, and I think in many other countries as well, math just isn't taught very well, if it is taught at all at the pre-kindergarten and kindergarten levels. There's a shocking number of teachers who just don't do math teaching. I have stories of our students being sent to supervision into some classrooms, and the teachers there often ask them to do the math program because they don't have any great interest in doing it themselves, which is certainly not a good message. And we romanticize what happens in Asia, but I hear that a lot of teaching there is not so great either. And so the outcome is that the kids who need help the most are the least likely to get it. It's the, I guess the 47% of the, of the kids who are, could use a lot of good math education, but are not getting it. And here's a quote from Maria Montessori, which talks about the educational concern, but also the moral concern. She writes, and this was, of course, a long time ago, she worked in the slums in Rome, before such dense and willful disregard of the life which is growing within these children, we should hide our heads in shame and cover our guilty faces with our hands. So it's not just that the kids are getting low scores that she's protesting. It's a willful disregard of the life that's going in them, meaning the intellectual development in this case. And it's not simply an educational problem, it's a problem of neglect. And so for her, math learning and other forms of cognitive development are very natural for children. That's what they do. They do amazing things like learn language. And we don't recognize that that kind of mental activity is going on in them, and so if we fail to foster that, it's a form of neglect. Another way of saying it is that math doesn't have to be poison. It can be, in Piaget's words, an aliment, a nutrition for the mind. So if we're not giving the kids the right mathematical nutrition, we are not helping them. And so what we do need is early, sound, effective, and universal math education for our kids. I know New York State, for example, has had, quote, universal early education, sometimes not funded. So that's a bit of a problem if you really want it to be universal. So then the questions arise, are little children ready to learn math? And by little, I mean, say, 3 years, 4 years, 5 years of age. And no, not if by math you mean traditional written math in boring form. But they do start with a lot of motivation, with some very good motivation, and with what we call in everyday math. I'm going to give you an example of the kind of motivation and interest you'll see. This is a videotape that we took probably 15 years ago now in a low-income daycare center that happens to be behind the Metropolitan Opera House. This is one of the great paradoxes of New York. So we have the housing development behind the Opera House. That's where we observed these kids. We made videos of them. And in this case, it's a kindergarten class. And so they're 5-year-olds. And what they are doing is totally spontaneous. The video quality is not great, but the content is. They're counting little beads, little stringing beads. Now there's a break. They kept going. He's got 100, he thinks.
3, 4, 5, 6, 7, 8, 9, 10, 11.
Now he attracts a whole bunch of female admirers.
57, 58, 59, 60.
And he didn't know the word 60, but somebody helped him.
63, 64, 65, 66, 67.
You notice that the girls are the ones fighting.
88, 89, 90, 91.
Stanley keeps going.
93, 94, 95, 96.
It rapidly deteriorates, but Stanley now goes on the floor to get his 100th bead. Okay, so that's Stanley and his crew, I guess. And so, you see that he's very interested in counting. A lot of kids are. And he's very patient. And he's very intense in doing this. And he doesn't let other people get in his way. And he's very careful. So you see this a lot. And when I saw that kind of thing in preschools I observed around the city, particularly low-income preschools, it really taught me that, yeah, these kids can do it. They're not the problem. The problem is how we teach them. Now, we do interviews sometimes to try to find out what's going on in their heads in a much more direct way than we can with these observations. So here is an interview with a little girl at age 4 about the 3 bears.
They went out for a walk. How many bears are there all together? 3 bears. Now, you know what? When they go for a walk, well, Goldilocks got lost. They're trying to find Goldilocks, okay? So they're out looking for Goldilocks. And you know what happened? They meet 2 more bears. There are 3 bears here, right? And they meet 2 more bears.
So we have a kind of abstract problem, semi-abstract.
And what about the other ones?
What's here now?
5, you sure? Let's see, here are the 2 bears that they met. Let's make sure. Are there really 5? You sure? Very good.
So she's dealing with a very simple addition problem. It's partly abstract. There were 3 that she started with, but then the others were in her head and in her body. You know, she was pointing 1, 2, 3, 4, 5. And this is, I think, a good example of what's now called embodied cognition and use of gesture. That's very important for her thinking. And so, you know, a 4-year-old has some very fundamental ideas about adding. She's not unusual. She may be more expressive than many, but this is the kind of thing that kids can do as part of their everyday mathematics. So we know then that the kids are ready to learn, but current textbooks suffer from many weaknesses. Even Singapore math, which is now very popular and generally very good. I'm just going to show you a couple of pages from Singapore math. Tell me, what is this a problem in? What do you think? Subtraction. These fishes are about to fly out of the addition. How many people think subtraction? And how many people think addition? Okay, so we have a lot of smart people here who are split pretty much. By my estimate, it was about half and half of those who were willing to commit. And so here is I cut out what's on the bottom. So this is supposed to be addition. I thought it was subtraction. I thought these fish are going out there, but it's supposed to be subtraction. Addition. It's not entirely clear, and if you are presenting this to, I think this is first grade, Esther, is that right? First grade. There's an English version or an American version of the Singapore math. And you got to remember that Singapore math is very good. And there are many other textbook series, particularly those in the US, which are even more confusing than the Singapore math. So we wanted to help, and so we created MathemAntics, which is a software program. And it is intended to be for kids from age 3 to grade 3, 3 to 3. It's supplemental to a regular curriculum, although I must say I hope someday it will replace them. We really can do without them. It covers material from very simple notions, very basic notions, more or less the same, through negative number in grade 3. And it's a coherent program in the sense that it is intended to teach the kids all the essential ideas about number, not geometry, not shape, not space, number, over that period of time. And we think that if they learn, if they did experience this whole program, that's, I think, everything they need to know about number. We can draw charts lining it up to the Common Core. That's the new game. Everybody lines up their curriculum. Whatever they have, it will line up to the Common Core. But we go beyond it, actually. The idea of doing negative number is not Common Core. We're more hardcore, I don't know. That we want to show that the kids can do more than they are expected to. And in Singapore, I believe it's 6th grade that they introduced negative number, not before them. So here are some examples. I mean, we work in local schools. We have a process where we design things. We ask the people in the Boston area to program them, to get the artwork done. They send it to us. We go out to the local schools in Harlem, for the most part, now in Chinatown and in the Upper East Side. And we try things out. We call them up the next day and say, you know, this isn't working. Please change this. It's this very complex process. We don't just sit down and devise the activities. I think most developers of apps, of math apps, just do that. They design something that they think is cute, but they really have no data about it and very little testing. So here's some examples. To compare this with Stanley counting. But in the upper left corner is a video of the interviewer, no, in this case, I'm sorry, of 2 children playing the game. So we have they are working on a laptop. It's facing them with a video camera. It is recording their faces and everything that goes on the screen. Okay? So they're supposed to find out how many.
Let's find data. One here. See?
So they're helping each other. One of them figures out how many,
Yeah.
the one on the right.
Good work. There are 5 animals.
And what's the farmer on the left?
2, 3, 4, 5.
Yes. Yes.
How many animals are there all
Wow.
together? Click on the number line as soon as you know how many animals there are.
So she's counting them.
9, 10, 11. Where's the 11 data?
So-
11.
So one of them figures it out, the other reads the answer. Now she's wrong, actually. I don't know if you figured that out for yourself.
That's not enough. Try again.
Oh,
11.
not clear. They think that they may not have chosen the 11.
Yes, there are 12 animals all together. 1, 2,
So you notice as each is counted, the whole set
6,
is shown and increases gradually.
9, 10, 11, 12.
And they see the numeral, the word, and the voice and the sound at the same time. So they're integrating. Here we have 3 types of objects. We have the real world of unreal cats, right? We have a number line, and then we have the numerical and written symbols. Okay, so those are some tools that I am going to show you those too. The one with the little chicks in a line is a lineup tool, which has the chicks line up right after another. We won't see that one, but we're going to see some others. So now here's a little more complicated case. He has earphones on because it's noisy in the school, so you can't hear what's being said to him, but it's to figure out how many there are. Now look, they went into the box, and we call it a tens box. He says 10 plus 5 is 15. Okay? And again, you can see in the corner that feedback, the written numbers and words and the spoken. Okay. Now what's very interesting, I think, about this is that the tool we use is a base 10 kind of tool. It's a tens box. And the goal of it is to get the kids to think about math in base 10 terms. Now this is a 4-year-old or 5-year-old. I'm not positive which. Maybe 5. All right. 5.5. And kids that age generally don't do addition in the form that this child has invented, in a way. In other words, if we help them organize the world of number by tens, and then there's some left over, well, we never said anything about addition. He was the one who says, oh, it's 10 plus 5. So the theory is they discover addition themselves in the course of doing enumeration. So here's another example. We're going to make it a little more complex each time. So he's wearing the earphones again, and it's saying basically how many pigs are there in the barn. So he figures out that there are 7. He clicks on the number line, and their kids are getting the experience of a number line from the very beginning at age 3 and 4. So now the doors close, and you click on the arrow, he's told, and a couple of pigs come out. Okay? This is an experiment that Rochelle Gelman, a very well-known psychologist, created. It's a situation. And so you can hear him a little bit counting on his fingers and holding up 5 fingers, I guess. I didn't quite see it. And then taking away a certain number. And we have students right now who are observing the strategies that they use, and it helps us to understand what's going on. And this is paused now so the student could kind of interview him. We don't envision this being done in the classroom this way all the time, but for us right now it's essential to find out how it's working. And it's very important also for kids to be able to tell you what they're doing and explain their methods. That kind of metacognitive awareness is very important, and expressiveness. So now and there you see a very explicit way in which we link the work that the child does on the fingers even with the mathematical symbolism. And we're not afraid to introduce the symbolism early if we do it in a meaningful way, and we think that this is meaningful. Here's another example. This is an older child, 3rd grade, and it's a multiplication problem.
I like this guy. Let's try 6. He has to walk.
So here's the use of the number line as a tool, not just as a method for indicating the answer.
1, 2, 3, 4, 5, 6.
She made a little mistake there.
It's 48. Click on it. 6 times 8. Oh, we gotta go back a little bit.
You can't go back, but what can you do to find out what it is?
It's 42 because
You jumped 8 times, but how many times are we supposed to jump?
7 times.
Okay.
So if we jump back, we
Okay.
can do 42.
So she seems to understand this number line tool pretty well. And you see how if she's wrong, it will tell her and there's going to be feedback. And why can't we go back one? I think we ought to allow the program to do that. We should fix it. No, not reset her. Let her go back right there. See, this is what happens all the time. We have an idea like that. And then finally, here's a really fascinating
They're gonna
one.
be over here somewhere.
The task is, let me explain,
Yeah, right here somewhere.
to find the number 3 on each of those lines. Now, of course, what's interesting here is that one is twice as big as the other. And we have control to make it 10 times as big or 3 times. We can have them tilted. We can have them moved to the side, whatever we want. Now, that's important because this deals with relationships among numbers. This is a kind of rational number task as opposed to simple whole number, as you'll see. And this girl is just wonderful, is a 3rd grader, and she's wonderful in her explanations of what she's doing.
And I'm gonna copy the top 2.
So she's going to copy it, which is not a good idea. But we let her do
I
it.
got it right on top of it. And,
Nice try.
See, the arrow wilts. It's not happy.
Oh, 3 was right there.
Oh, so
I was
there's
close.
orange in the same spot, but you're close, yeah. And this one, look, right on.
Abby
So
got
here's another one.
7 is okay, so let me do this one first. It's kind of easy. So 10 might be right here. No, wait, no. Yeah, 10 is right here.
So the strategy is find the middle and go a little bit in the right direction.
Mm-hmm. Now what about the top one?
Top one for 7. I'm gonna count from here.
Okay? So 7 is closer to 10 than to 0. So you kind
No,
of,
it could be.
well, go further. Go further.
Uh,
Good
Didn't work.
attempt.
see,
Oh,
I'm
you're still
almost,
pretty close, yeah.
that one's just a little bit harder.
Yeah.
Just a word about the red line. See the red line? That's a kind of region of acceptable answer, right? We can make it narrow or wide. We can create devilishly hard and interesting problems this way. We can set it up so that if you are accurate with a very narrow band, you're going to get more points than if you are very conservative and use your wider band. So it's about risk-taking, it's about many different things, and it's really fascinating. And it's about approximation. And what do we mean by mathematical approximation? The gray arrow is the wrong answer, where the child indicated.
Still got 90.
Right.
10 is right here.
Easy.
That's easy.
And this one is easy too. It's right in the middle.
Okay. So she knows something about these relationships, about 10 is halfway between 0 and 20. And that's a very important idea.
And 30.
And so we can study how kids learn in this situation over many trials, many experiences.
Down, right here.
And that's pretty good.
And this one, since 10 is in the middle right here, move it down right there. Yes!
Pretty good.
Oh! And that
And-
one's like right on top.
And she started out by copying them exactly, right? Okay. So these are just a few examples, but I think we could say some things about why software is useful and how it can really transform math education. One thing it can do is allow for exploration. You can play with, we can set it up so that kids can play with all these different activities. Kids love to put out large numbers of things, right? I do. I like that we have an egg maker. We have a machine that makes chicks. And so you keep clicking on them, the screen fills up with chicks. I find that very charming. You can explore. You can use the tools then in any way you want. You have 100 chicks on the screen, and you can then explore with the tens tool. You can have the lineup tool, all sorts of things. This is dynamic, not static. So the page you saw from Singapore Math is static. It's very hard to portray movement on a two-dimensional surface like that. Whoops, did I? Sorry. But this is dynamic. When something is added, it's really added. When something is taken away, it's really taken away. It allows children to do things they could not do otherwise. So if you've got a whole bunch of objects on the screen and you hit that tens box button, you can rapidly organize them, and you can't do that so easily in real life. Now, of course, kids, you can do that with manipulatives to some extent, but teachers know if you've got 200 manipulatives on every desk and kids are going to be playing with them, it's a recipe for disaster. It's just not very efficient. And I think one of the most important cognitive things is that it connects the different representations of number. So we have chicks, we have boxes, we have number line, we have symbols. And they're all talking about the same thing. And this is how kids are, we hope, will find that math is a very meaningful activity. So their informal ideas about adding and subtraction, which we build on, gets supplemented in a very deliberate way by these abstractions. It gives them useful feedback. And you saw in several of these examples how, yeah, they're going to find out whether they were right or wrong, and they're going to be given more of a chance, they're going to be given a chance to do some more. And we can target the feedback in various ways. It doesn't have to be only right and wrong. It can be, oh, did you try to count them? Or check your answer. We do that in the barn with the pigs coming in and out. We have a condition where we can open the barn door and say, check your answer, try to make sure. And you can provide the teacher and also parent with useful reports. We can find out the internal workings of the software can identify whether the child, for example, has clicked on that tens box as a method of solution. That, I may get the answer wrong, but the fact that he clicked on the tens box is a good indication that he has that strategy, that he believes that strategy can be useful. And of course, if we see this reliably, we can make some good inferences. And the computer software then gives you a report after the thing is over. It can tell you every single move the kid made, every single problem, what they did, and it can extract some interesting information about strategies and concepts. So I think that's pretty good if we can do that. There's still a lot more to do, but I believe that this software approach can be extremely helpful for our little kids. Thank you.
But what about when, bringing the parents in onto it? I mean, is there something set up to bring the parents in so they maybe also assist or,
Right. I mean, it's a great idea, and right now we have not been doing that. But in fact, the parents of young kids are not that different from the teachers in terms of their knowledge of math education. So I don't see why the parents couldn't do a lot of this work with their kids, particularly in the very young ones from age, say, 3, 4, or 5. When they get into negative number in third grade, some parents are going to feel uncomfortable. But we definitely want to do this in the future, and I think it's going to be particularly useful at those younger ages.
iPads and iPods, and I believe that in this software are you using the mouse exclusively, or?
It's very interesting. I wrote the grant for this about 3 years ago, before there was the iPad. And it did not exist when I wrote that. And in 3 years, it's totally revolutionized. So we absolutely want to use touch screens, and we have started to. There's an interesting workaround method that Ozzy over there has created for helping kids to work with touchscreen. But if you could imagine so we have all these chicks on the screens, and the kids could drag them in a straight line, could drag them into the boxes, could put some on top of others. I mean, so it opens a whole world of gesture, and it's more, quote, manipulative in the literal sense. Manipulative means you're using your hand. And they can use their hands. And there's some evidence that even if you put a boundary around several objects, you sort of create a set, that action of doing this has some cognitive power. So what is a set? It's when you make a circle around these objects. There's some boundary around. So it's very promising, and we definitely want to do that as our next step.
Working with older students, do you use these types of visual aids to help them in understanding this?
I mean, we've gone up only to grade 3. But as you saw in the example of the double number line, we're starting to get into those ideas of half and so on. So you can imagine using the number line as a way to teach about those fractions. And that's something, there's so many things we started out to do that could be elaborated in many ways. You could also, if you see those boxes that we use, like the tens box, we also have a ones box, a two box, a three, and so on. You can imagine teaching fractions in the context of those rectangles, basically, right? So, you know, 4 blocks are half of 8. And there are also, and 2 blocks are half of 4. Now, in what way are those two things the same? So the boxes give us kind of an entree into simple notions of area and can be used for things like fractions, as you're mentioning. They got to buy a lot of computers. And they have to, I'm serious, they have to get touchscreen devices like the iPad or other notebook type things that are not that expensive. I was at a conference recently where somebody from India was talking about, oh, he could make those for $40, $50 each. And textbooks don't cost a lot less than that. Plus, you could take these devices with you from grade to grade. So there would be some savings that way. But they will have to change that. But these iPads and similar things are so extensive now. I mean, they're so widely used now that it will seem quite natural in 3 years that every kindergartner ought to have an iPad. As part of our work, we have been reviewing a lot of apps from the iStore. And we have, I don't know how many now. I keep getting these bills in my iTunes account. Some of the students are buying these things, quite a lot. I think we have at least 70 or 80 or 100, Ozzy? 120. So we study them, and we have a serious method for evaluating them that Ozzy and Samantha have contributed to a lot. And we find that a lot of them are just not that good from from an intellectual point of view. And a lot of them are rote drill, essentially. You know, it's shooting down a rocket, so you get a lot of violence, and you get shooting down a rocket. You know, if you got 2 and 2, you shoot down the rocket, the plane that has 4 or something, all right? So you get a lot of that. There are some things that are pretty good, but what they lack is a systematic development from point to point. They're kind of like random things at different age levels. They don't build. And I think what distinguishes ours is that it will build over time. It's coherent, both in terms of the development of the ideas, the mathematical ideas, and also development of kids' thinking. Almost everything we've designed has elicited things that we weren't looking for. I mean, if we were to narrow our focus and say we just want to teach number facts in a rote way, I mean, we could do that. We could design it very tightly, and we wouldn't learn a lot. But our software is much more open-ended, and even though it is structured, there's still a lot of room for kids to do things we didn't expect. So we keep in mind a kind of general rule, which is that kids say the darndest things, isn't that the old phrase? And that we're going to find unexpected things, and that's great. And if we find them, sometimes we'll have to modify the software. It'll suggest new activities to us. So we try to exploit that. It's not that we're designing something not to find something else. We're targeted on some big ideas, and the normal thing is that they proliferate. And we have to be careful not to go in too many directions. I think the phenomenon you're pointing to is that in different cultures, we have different kinds of everyday mathematics. So I once did research a long time ago in Africa, in the Ivory Coast, working with merchants who were illiterate, but whose mental math was very, very impressive. And what you're talking about might be something like that. So if we have not worked with different cultures so far, but it would be very easy to translate our mathematics into any language, because the words that go along with it are like little audio files that are very easy to put in the program, and the written stuff is also very easy to put in. So it's trivial to, almost trivial, It's not trivial for me, but for somebody who knows this, it's not hard to make forms of this in other languages. And so we could study this cultural phenomenon. And yeah, you'd probably do some things differently in certain cultures because of what you know about how they develop their everyday math.
Together.
I mean, eventually they certainly have to group things, there's no question. You got to do it. You have to learn the base 10 system and other ways of grouping. I mean, you have to consult the research literature on this, and there is a developmental literature which shows that over time they do indeed develop methods of grouping. I don't know what kind of sample you've seen, but the evidence seems to be that grouping is very natural. It does develop in kids. They get that idea, and it can be very useful. And they got to do it if they're going to learn math. I mean, in general, there is work now on social interaction as one method for promoting intellectual growth. And we know that when kids get into productive arguments with each other, this can be very helpful. There isn't as much done on the effects of slightly older kids teaching younger ones. I think it's a great idea. And we want to set up MathemAntics so that it can be used in classrooms by pairs of kids, by small groups of kids conceivably, by the teacher on the smartboard as a way of introducing it. So having social processes built into the learning experience could be extremely valuable. I think using it in a whole group does not necessarily mean that kids can't then go on individually using the software. So the way I would see it is that you start out in a group and you get everybody kind of used to this is what you do with a box and all that, and you can call them up and they do simple problems and they talk about it. And then you're absolutely right. You will find that some kids are at many different levels. All the kids will be at different levels. But the advantage of the software then is that it's adaptive, so that it will automatically level for kids with certain abilities.
Okay. So, and the related question is, somebody asked and you said depends on the older kid and adult. There's a way that things get introduced and it gets killed because the person doing it has no clue.
Yeah.
So I'm wondering is how could somebody mess this up, Do you have you seen that happen? And
Well, oh yeah.
Sure. Yeah.
Teachers and parents can mess up almost anything, and so can other kids. No, really.
Yeah.
And so we have to be aware that that's a definite possibility.
What would that look like, messing it up, for example?
What it looked like could be teachers misinterpreting the need for the different kind of tools and how you use them. It could be giving the kids problems that are not appropriate to start with on the whiteboard. One argument for using software is that it can bypass teachers of the type you described. I mean, there used to be the argument, let's get rid of the teacher entirely, and the computers will take care of everything. Kids don't need to see the teacher at all. A teacher can't harm anything. I really don't believe in that. I think the teachers can have an important role with the kids, but it can be a very different role where, yes, they can do some of the group activities, but they need to then have the ability to work with individual kids to address the kind of problems that those kids might have. And the computer might give the teacher a report. So you ought to help this kid with so-and-so. And so I can picture the teacher going around the room as kids are working apparently individually or in pairs. And it'd be a very different role for the teacher. But we do know from the research that math talk is correlated with success in math. So the more you can get the kids to talk about what they're doing, to use the vocabulary, and it's not just learning words like hexagon, which is fine, but it's learning, oh, this is a hexagon because it has blah, blah, blah. Or you couldn't possibly, if I'm adding 3 and 1, there's no way I can get an answer of 1 because, right? So that kind of talk, the teacher needs to encourage that kind of talk. And we know from the research that parents who do this more, who encourage this with the kids, have more successful kids in math with respect to math achievement. So literacy, I mean, I love to talk about this with teachers and tell them that math is a kind of literacy. And we haven't done this yet, but in MathemAntics, we want to have storybooks, interactive electronic storybooks that introduce concepts within a narrative and let kids interact a little, use the software embedded in the book to do certain things, and then graduate from there to the more pure version of the software, if you like.
So please join me in thanking Herb Ginsburg for this, for your conversation.
Equivalence, more or less.
Guaranteed seeing this program and then jumping.
Like, you click on the number 5, right? And it will rearrange so that it's an array of 5 for a group. Then she can count 1, 2, 3, 4, and press 20. And that shows that this is 4 rows of 5.
And I work in a school system, so I'm looking forward to seeing how we can get some of our teachers in my school district to use the software.
We're currently bringing in a lot of iPads and applications for teachers to use in the teaching of mathematics. What this program tonight made me aware of is how important it is to really look at the quality of the program rather than just the fact that you're getting apps to use the iPad or to use the computer.